Now, I brought 4 lectures, and I have 4 days, but my 4 lectures are not equal in length. And just as on the first day, I finished my first lecture, and then got into on the solar system, and then started on planet formation, because I had a long planet formation. My plan was today go through exoplanets and start Kepler. But since I wasn't feeling well yesterday, I still in the morning didn't have time to do the full 90 minutes. So I'm taking that extra 15 minutes that I missed in this morning and giving it now, when I recovered a little more energy, to introduce you to Kepler. And this is one of the signature graphics of Kepler. It's an artist's conception of the Kepler 11 system. And as I mentioned before, with artist conceptions, there's some artistic license. The star Kepler 11 is like a sun-like star. This is actually a picture of the sun. And a picture of the sun when it was spottier than usual because it was prettier that way. And then there were actually 3 planets observed to transit at the same time. And this is their relative positions to the center of the star. Although we don't know whether they're above or below. We could get the angle, the impact parameter of the transit. The sizes of the planets are all correct relative to one another, but they're magnified by a factor of 2.5 to 3 relative to that of the star. Again, artistic license. And while these 3 planets were indeed transiting at the same time, these other 3 planets, they wouldn't even be, or at least 2 of them would not even be in the building, huge distances away. But we did have the right sun angles. If they were in these positions, they would either be almost on the other side or almost transiting. Kepler is capable, if we're really lucky and it's around one of the brighter stars, of detecting a true Earth analog. We haven't done that yet because it's really the borderline case with all the Kepler data, and there's still a lot of analysis that needs to be done. But we're by far the closest in terms of size and position of anything that's been found. And we're getting very close for smaller stars of having an Earth-sized planet getting the same flux of radiation that an Earth has. The principal goals of the Kepler mission are statistical: to conduct a representative sample of the planetary population within our galaxy, out to and including true Earth analogs. Bigger planets, those closer in, are easier to detect, so we have much better statistics. Again, this planets like Earth in front of sun-like stars, detecting that by transit means you need very sensitive photometry, very sensitive measures of light. The atmosphere is a real problem for that. That's why Kepler is a space telescope. Transit data from the duration, depth, orbital period, and inclination, or tilt. We can only see if they're just nearly edge-on, but we can determine the degree at which they're apart from exactly edge-on. And from the ensemble, from individual ones, we get planetary sizes and their orbital semi-major axes from Kepler's third law, and that's why the mission is named Kepler. We get the frequency planets, and we need a lot of stars because especially, well, for these close-in hot Jupiters, 1 in 10 transits but for an Earth, only 1 in 200 transit, just because Earth's farther away, purely geometrical factors. So you need a lot of stars. And this is the transit light curve that I showed before, early this morning. Kepler looked at about 160,000 small stars at a time. 140,000 were observed for almost the entire mission. There was some cycling of other targets. And what we did was we recorded measurements of all the brightness of each of the stars every 30 minutes. And because of downloading we're turning the spacecraft to download data and a few minor glitches, our duty cycle was around 90%, not 100%. But we did incredible precision. For the brighter stars, we got better than 40 parts per million for 6-hour intervals. So 1 part in 25,000. And Kepler mission goals were determined to determine how common terrestrial planets are in and near the habitable zones of a wide variety of stars. So that's the big astrobiology go. Determine the distributions of semi-major axis and size of these planets, estimate the frequency and orbital distances of planets in multiple star systems, binaries, determine the distribution of semi-major axis, albedo, etc., characteristics of the short period giant planets, because our photometry is sensitive enough to get those changes in light that I showed you for one of the planets this morning for the close-in giant planets, maybe even for one close-in rocky planet that's around a particularly bright star. Identifying additional members using complementary techniques, which means radial velocity. In some of the systems we have found non-transiting planets, including giants, at greater distances using radial velocity. And then determine the property of those stars that harbor planetary systems. That's, for some of the bright stars, it's done by measuring the seismic variations, stellar oscillations. If you've heard of helioseismology, the study of oscillations of the sun, this is the stellar component counterpart. But we only have enough light to do it around the really bright stars or the giants, and the giants we're not seeing planets around because they're just too big. In the other cases, what we've had to do is use spectrum obtained by telescopes from the ground, because Kepler is just one wide bandpass. This is a spacecraft and instrument. We have an engineer here for scale. This is a relatively small telescope, much smaller than HST. Budget less than a tenth that of HST. The key thing, very big, very wide field of view, 10,000 times the area, more than 10,000 times the area of HST. CCDs, just like in your phone, but a little bigger area than in your phone. And again, engineer for scale. And this is just how the spacecraft is arranged, and some of the technical details. Photometer, basically a telescope which is gathering light. It's not spectroscopy, just the total light. It's a very wide field view telescope. The aperture of the corrector, which is how you use how you define the aperture of a Schmidt telescope, this wide field of view, is about 1 meter in diameter. It's actually, I think, the 10th largest Schmidt ever built. that was launched into space. By far the largest wide field of view telescope in space. These are the individual CCDs of the electronics, the focal plane. This is where we looked near the midplane of the galaxy and just off the midplane, because we want a lot of stars, but we won't want too many stars because then they're too close and they confuse one another. And this is in the northern sky, so people in the United States can go up and look, point out where it is, but also, since most of our telescope assets for doing follow-up are in the north. This is another view. We managed it, since the bright stars would cause a lot of glare, diffraction, spikes, etc. We put them between our CCDs, the brightest stars in the field. Here is the telescope inside the rocket. Launch. The orbit, it was escape Earth because you don't want all the thermal variations from being in eclipse from Earth. You want it as stable as environment as possible. The Europeans have been using the L2 outer Lagrangian point to get these advantages. This is a low budget mission, so we didn't have the second rocket boost, motor to slow it down and keep it in station keeping around L2. So we just launched it into an orbit. It's a little farther from the sun. It's drifting away because it has a 372-day year, so gradually moving farther from Earth. This is what an image looks like. We generally don't send down the full data. It's a galaxy. It's not that pretty, not a high resolution, because it's a very large field of view. The data can look kind of messy, but and we don't actually have that accurate photometry. We have precise photometry, which means relative accuracy. So from one time step to the next, it's very, very consistent. So we can measure these variations. These are the first 5 planets we discovered: a hot Neptune and 4 hot Jupiters. They are not the most common, but they were the easiest to verify, because at that time we had to use radial velocity and measure the mass of the planets. A lot of this has been done at the Keck telescope. These are the radial velocities of those planets. And this was a lot of time, but we wanted to get one non-hot Jupiter at the beginning. And I'm going to end for today, so we can have discussion with this, which is a diagram showing, as of almost 3 years ago, our Kepler, our planet candidates. We now have almost twice as many as this in the actual sizes relative to their stars, the stellar sizes. Tremendous number of planet candidates. And I'll go into details about what we found out about planetary systems from these data tomorrow morning.